Uh, can I say, okay. Hello, everyone. Um, I am Jun Du from University of Science and Technology of China, and on behalf of my team, today I will introduce our system. And this is the joint team to complete this system, USTC and iFlytek Research and Georgia Tech. And this is first I will give you a quick look at our system, and it mainly consists of three parts. The first is a front end. Front end we use a 6-channel beamforming, 2-channel beamforming, and also we use a single channel noisy data to have a training data augmentation. And the second part is acoustic models. Acoustic model, we use deep neural network and deep convolutional neural network. And and for the language model, we just use the LSTM language model. For the recognition, we for different channels, for 6 and 2 channels, we just use a 6-channel and 2-channel beamforming, use the same method. And for a 1 channel, we just send the noisy input to the feature extraction. Also, the second part is acoustic models. We use for the 6-channel, we use the 5 neural networks to perform a state level fusion. And for the 2-channel and the 1-channel, we use 2 additional models trained on the 2-channel beamforming data. And in total, we have 6 models for this 2-channel case. And the language model, we first perform 2 parts. First pass we use 3-gram, and the second pass we use only use LSTM language model. We do not use the 5-gram or simple RN to have average, because we see that that will decrease the performance. We just use LSTM language model for the second pass decoding. And for the overall implementation, we first use the official KLD recipe to extract the FMR features and log mail feedback features, and we train the baseline DN HMM acoustic models by concatenating FMR and log mail feedback features. And the model ensemble and 2-pass decoding, we also use the official baseline recipe. And we use a CNTK toolkit to train the IIMDN. We will introduce later the training. And for other part, we we self-developing some tools for beamforming and deep convolutional neural network for acoustic model only with cross-entry training and the LSTM language modeling. First, I will introduce the very important module for the beamforming. And our beamforming is use a concept of a feedback loop optimization. We do not just using the signal processing method to do the beamforming. We also combine the single channel deep neural network based speech separation methods, and also we combine the first pass recognition results to improve the beamforming. Mainly, first on the left, we use the DN-based IIM estimation to estimate the T time frequency unit IIM, and the left we use the recognizer to perform a segmentation of the noise and the speech segment, and all this information will sent back to the beamforming to perform a second pass beamforming. And I will introduce the beamforming later. First, I will introduce how to train this DN-based IIM estimation. We just use 3 hidden layers with 2048 hidden nodes, and the input feature is the log power spectral features, and yeah, with seven frame expansion. Yeah, and the output is the TF IM, and for the input we use the channel 5. All the both the input and output data we use the simulation data. Yeah, because for the real data we do not have cannot calculate the target. We just use the simulation data, and the input is channel 5, and output is TF-IM between the channel 5 and the clean underlying clean speech. And yes, okay. And this is the beamforming part. Beamforming, we have 4 steps. First, we just for 6 channel case, we use this channel selection to abandon some bad channels, and then we use the complex GMM method from the NTT to perform to calculate masking, and then to calculate the noise and the noisy covariance matrix. With that information, we performed in the third step. We performed the GSC-like beamforming. Yeah, use a reference method, and finally we do the post filtering, and the VAD information and the DNIM is mainly to improve the masking performance for the CGMM-based masking. It's the second step. And this will give a spectrogram comparison between the officially provided beamforming and our proposed beamforming. You can see that for this strict example, the channel 5 input, the official provided beamforming do not remove much noises, and our approach can is more aggressive in reducing the noises. And this is a recognition result, and we can see that we give both the result of the real development and the real test set, and compare with the officially provide the method. Our method can have a significantly error reductions. Yeah, and for 6 channels, the improvement is much more. Yeah, and our conclusion here is that our beamforming method is more effective for more adverse environments. So you can see that for the development set, the relative reduction is smaller than the real test set, because the baseline is already very high. So our method is do some aggressive noise reduction for the the adverse environments. And with more microphones, you can see that the improvement is more significant. And this is front end, and then I will talk about the acoustic model. The acoustic model first is the training data. Training data, we use data augmentation for the 3 case of different channels. We use a multi-style training. A stand for the one channel noisy speech. Yeah, we use 5 single channel speech, except the channel 2 is very noisy, to simulate the one channel case, and the 2 channel beamforming beamformed speech to simulate the 2 channel case, and the 6 channel beamformed speech to simulate the 6 channel case. And for training the 6 channel model, we use A and C data to train 1 DN and 4 DCN. And for the 2 channel and 1 channel case, we use additional acoustic models. Use data B and A. And this is the configuration of our acoustic model. The left is the DN HMM model, and we use 7 hidden layers with 2048 units. And yeah, and input we use concatenating 3 features. One is FMR and log mirror feedback. Also, we use the iVector features, 20-dimensional iVector features. We see the complementary of the iVector and the FMR, although they are both adaptive, the features. In the right, you can see that we use a deep convolutional neural network. It seems like a VGGNet. Yeah, first we have 4 blocks. Each block we have several. Use 6 nets. Each net is a convolutional layer. Yeah, with batch normalization and ILU activation function. And because we for the input, we can use the FMR or log mirror feedback, and we also can use the 3x3 or 3x5 filters. Then we can have 4. We can train 4 DCNs. Yes. Yes, this is performance of the COSI model and the ensemble. The blue one in the left for each channel is the DN HMM baseline performance, and the red one is the DN HMM, just a single DN HMM system by concatenating FMR and log mirror feedback features, and we can see that this single system have already also with training data augmentation. Yeah, this already have about more than 30% relative error reduction, and the finally system by ensemble we can have about 50% compared to the DN baseline systems. Yes. Finally, it's a language model. Language model, we use the conventional LSTM language model, use LSTM plus projection layers, and we also use one fully connected layers to the output. And here we use 2 LSTM language model. One is forward, just modeling the text from left to right, and the backward LSTM from the right to left. We can have 2 models, then the recognition can be combined at the lattice level. This is our LSTM language model compared to the officially provided 5-gram plus RN language model. We can see that with more channels, the improvement is more significant. Yeah. This implies that if you have a better backend or acoustic front end and acoustic models, the more effective is the LSTM language model is. Yes. As a summary, we listed the result here for different environments and different test case. Yes. That's all. Thank you.
We have time for questions.
I have 2 questions. One is I'm a bit surprised that your VGGNet still works well with the FMR feature, but we know filter bank is more appropriate for the convolutional neural nets. So another question is, look at this result. Your single VGGNet is even worse than the DNN. Why?
Yeah, it depends on different testing cases. Yeah. We do not have more analysis on the input features on the with different neural network type. We just we found that after the ensemble, the performance is more stable. Yeah.
Okay, so you mean the single VGG result is worse than the DN, but it can get a good complementary with the combination.
Yeah,
based on your results.
I think for the DCN, different input features may have not a big impact. After the, I want to show from this result to this, just want to show the effectiveness of the model ensemble. And for different models, I think it varies. It depends on different. For example, the trend is different for different channel case. We do not have much analysis on this. We just focus on the final ensemble models.
Okay, I see.
Yeah,
and
yeah.
my first question is why use FMR for the convolutional neural nets? How about your results?
Why use FMR?
Normally we use filter bank for the CNN.
Yeah.
So how about your results using these two feature?
We just from the DN network. Yeah, we maybe it have some problems for the modeling the FMR features, but we do not have.
Okay.
Yeah. Yes.
I see.
After ensemble, this change is not that significant.
I see. Thanks.
Yeah.
So I think we have time for one or more, two questions. So.
So the ensemble seems to be very, very powerful. So I'm very curious. First, you just averaging the posterior, or how did you make?
State posterior averaging. Yeah.
I see. Without some kind of weighting or running some weighting, just averaging.
Average. Equally average.
I see.
Yeah.
I see. That's pretty interesting. Yeah, but you guys already showed that in the previous CHiME series, right?
Yeah.
So
Yeah.
that also has a similar gain that the ensemble of this kind of techniques usually works.
Yeah.
Okay, that's very good.
Okay, maybe one last question.
Just wondering how the VAT frame result from the ASR is used in the beamformer.
What?
If you go back to your block diagram, or the frame VAT, how do you use it exactly in the beamformer?
We just use this to segment to determine the noise segments. Yeah, we first use the VAD for the second pass beamforming. First, we use the VAD to determine the noise segment. Then the DNIM is applied to the speech segment. And those information can apply to calculate the masking. You can consider that these two information is to improve the masking performance. Yeah, I think frame level VAD is to determine the noise segment, and the IM is determine the speech segment. Yeah, because this is the TF units, is with high resolution. Yeah.
Okay, so I think we have to move on. So let's thank the speaker.